Welcome back. So now we start on section 5 to volumes. Let's recall volume of a rectangular box. So that's a rectangular box. Length L, width W, height H. Volume of the rectangular box is length times width times height cube units. All right. Volume of a right circular cylinder. Right circular cylinder. Right means it's perpendicular to the base. Circular means the base is a circle. Circle of radius r. Height h. That's the perpendicular height, right? So volume of a right circular cylinder is V is pi r squared h cube units. Pi r squared is area of the base times height. That's the volume of a right circular cylinder. So notice you may view rectangular box also as area of the base, that's length times width, times height. So base, area of the base times height. For a right circular cylinder, area of the base times height. For a right cylinder over any region, so you take any region, any shaped region, a right cylinder means you are taking perpendicular height. You are not slanted. It's not an oblique cylinder. It's a right cylinder over any region B. So region base has area B. So volume is B times height. So area of the base times height. Which brings us to, what about an arbitrary shape? Look at that. That's an arbitrary shape. So this shape is similar to this shape, similar to this shape, this shape. So what's going on? I'm taking this shape. It's not a cylinder over my base, but it is some kind of an expansion and then contraction, you see. So when you have an arbitrary shape, what we do is you approximate. Well, how do we approximate? You take slices. You take slices of thickness delta x. Thickness delta x, and that's one side and the other side is behind. You see? So notice the small slice is now a cylinder. Cylinder over this base. Say that base area is A of xi star. So what is A of xi star? So you probably now recognize I'm looking for a Riemann sum. So this entire solid is supported on this line from interval, closed interval A to B. You're going to divide A to B into smaller subintervals. This is my ith subinterval. Above that ith subinterval has width delta x. You see, each subinterval will have width delta x. So over this is this particular region. Over this point is the back region. So what do I have? Over this interval, I have a thin cylinder. That cylinder has width delta x and base area A xi star. I'm using xi star because xi star is any sample point on this interval. So that would be the volume of that one slice, AXI star times delta x. AXI star times delta x. Now you sum such volumes, take several slices and find volume for each slice for n of those, because you're going to have n subintervals. You're going to get n thin cylinders whose volume is base times the height. Height for each cylinder is delta x, is the base area, which will change as per your choice of point on your on your interval beneath, you see. So this is your Riemann sum. So notice we are taking slices, many slices. So this is, the summation is an approximation. It's not an actual value. It's not the actual volume, but it is an approximation. So as an approximation, you have a Riemann sum over n slices. So, which brings us to the actual volume. So by now you know, if you take limit n approaching infinity, that is, you are taking many slices, in many slices, that limit would be the limit of this summation would be the actual volume of the solid. So here is your definition. Let S be a solid that lies over an interval A to B. Suppose for each x in this interval, the cross section, so cross section is this face that you get. When you slice it, you get to see a picture, right, on the side. That's called cross section. For each x in your interval A to B, you slice it, you get cross section. Let its area be AX, and you want the function AX to be continuous. Then the volume of S is given by, volume is the limit of the Riemann sum, summation I going from 1 to n, AXI star times delta x. So notice we are here using volume of a cylinder formula, base area times height. So for each small slice, you essentially get a cylinder. So you're finding it, the volume of each cylinder, adding all of them, and you let the number of slices go to infinity. This is essentially integral A to B. This AXI star becomes AX. Delta x, you write it as dx. This comes from the works in chapter 4, all right, in calculus 1. That is your volume. So now we'll start with examples. So remember, volume, you are going to take integral A to B of the cross-sectional area function. All right, cross-sectional area. So what is cross-sectional? You take your solid, slice it, you get a cross-section. That picture, that base, its area. So for each x, you get an area. Here is area small, then it seems to increase and then it decreases again. So area function could change, right? But that area function you use, dx, integral A to B. That result, if it exists, well, if you're continuous, you should get it, will be your volume. All right, so next video we'll start on examples.